The title, it says Discrepancy and Adaptation, and view this more like a tutorial on this topic, both related to adaptation and a crucial, in my view, notion that of discrepancy, which I will describe in a few minutes. I will also, of course, discuss some more recent work. So, I think, feel free to come and sit here if you want. So, much of learning theory and learning algorithms are based on the following assumptions, which I think are meant for an ideal world. This is a world where the distribution for training and test are the same, where the distributions are fixed over time, and where the sampling is IID. All of these, of course, are natural assumptions. Without some of those, in fact, you could say, is it even possible to learn? If you've gone to some other workshops here, you would imagine, even if you have these, sometimes you could wonder if it's possible to learn. So it means that you sort of, it is natural to make those assumptions, but the real world is really quite different. If you think about it, this is the ideal world of learning theory and much of past learning theory and algorithms. And the entire space otherwise is the real world. So in fact, in practice, when you're trying to tackle a new learning problem, you're never here almost, okay? So I've tried to sort of describe these three axes that I think are important. One is the domain. So in some sense, quite often when you're dealing with a real-world problem, the source domain that you are that is available to you is quite different from the test domain. And really the main reason for that is in fact the dollar sign. The reason is you want to learn for prepare a learning algorithm for a new domain, but you just don't have the resources to have label data for that new domain. So you're doing the best that you can do with whatever you have, the label data for a source domain. Another one is drifting. Distributions change over time. So a classical example for that is spam, where spammers actually change their distribution, they change the way they are producing spam. But in fact, you see this in a variety of other problems as well. By the time you're finished preparing your learning algorithm, you have good results at a particular problem, things have changed already. And if you're working for, companies where data keeps coming, I don't know, credit card companies, fraud detection cases, insurance companies, search engines, data keeps coming, and by the time you've finished something, there's something else that's coming. Okay? Things have changed. So how do you manage to adapt over time? This is another dimension of adaptation. And then there's another one, which is that of sampling. So I mentioned IID sampling, but there's sampling of, whenever sampling is different from the ideal sampling, you have adaptation problems. There are other axes that I'm not mentioning here, which are, for example, the fact that you may have several sources, several domain sources. This talk is going to focus mostly actually on this axis, that of domain adaptation. Although, in fact, we have done work now on all three of these axes, using, in fact, very similar ideas, which I will have to report elsewhere. So let me start by mentioning what the domain adaptation problem is. I think Afshin has already mentioned that, so I will go very quickly on this. It's the case where the source domain is different from the target, and you see this in a variety of other problems. Application sentiment analysis, where you have appraisal information for some domains, think Amazon domains, movies, books, music, but you have maybe no label for, say, travel. Okay, so you want to make use of label data here to make predictions for a new domain that would be travel here. And then classically, in fact, in natural language processing, adaptation has been a problem for a while, because this is natural language processing is a place where people have been doing actually a lot of work, and in fact, quite often learning ideas are coming from there. So in language modeling, speech tagging, statistical parsing, speech recognition, computer vision, which is a different one, in all of these areas, the adaptation problem has been already addressed in some ways, but perhaps not as much in a theoretical way, which Afshin was talking about before, and much more in a sort of ad hoc manner. And in some ways, I would already start criticizing some of the work that has been done here in natural language processing, for example, for adaptation. Well, although it might work in practice, part of it has no principle. Okay, there's actually no theory for why it should work that way. So it's basically tossing a coin. You'll see that part of this might also affect what I'm going to say, so I should be more careful. So I do want to mention one thing. Giving a solution to these problems is critical. Some people think that adaptation is just a little problem, or these learning people are trying to come up with a new problem that maybe a few little people in a corner would care about. That is not the case. It's a major, major problem. If you don't address it, it's not going to work. It is just not going to work. The performance is going to be terrible. And for all three of the axes that I mentioned. So let me just formalize this a little bit more. I'm going to talk about a domain as a source domain and a target domain. The source domain is made of a pair, a distribution Q over the input space, a target function f sub q, which is the labels that you receive for that domain. And similarly, a target distribution P and a labeling function f sub p, which are again the true labels you wish you could have received. And the problem is formulated in the following way. You're receiving a labeled sample S drawn from the source, so drawn from this distribution for the input, and with the labels that are from f sub q. And typically a relatively large unlabeled sample from the target, because unlabeled sample is, unlabeled points are cheap, so you can imagine that this one is typically much larger. And the problem consists of finding a hypothesis H in some hypothesis set A, in capital H, that has a small expected loss with respect to the target domain. So that means with respect to the distribution P. So this is going to give me the opportunity to define the notation as well. I'm going to denote by the calligraphic L sub P, the expected loss with respect to the distribution P, and then of the loss of the first element with respect to the second element, which is really what you care about. Okay? So it should be clear that this is a challenging problem. It's at least as challenging as the usual learning problems, but it's more because you're getting a data from a completely different distribution. So there's been a lot of work in adaptation, as Afshin also mentioned already before, in a variety of domains. I'm not going to cover the previous work here, but only talk about some of the theoretical work that has been done here. Much of that has started with the work of Shai and John Litzer here and several others, who were the first to tackle this problem by giving VC dimension bounds based on a dA distance and a term lambda sub h that is not accessible, that is not possible to estimate. So I would say that these are really nice because this is the first time, I guess, this problem is even addressed. And particularly the use of the dA distance, which is going to be related to the discrepancy, is very crucial. But there's a bit of an issue to say what we refer to as being a 3 times the error issue with these bounds, which basically means that there's 3 times the loss of the hypothesis with respect to the FP, which could make these bounds sometimes non-informative in some cases at least. And then in some later work, we gave learning bounds for this adaptation problem based on the notion of discrepancy, which generalizes this, and that I'm going to describe in a few minutes. And our bounds are also based on a quantity that sometimes you cannot estimate, which is related to the optimal hypothesis, so it has the same issue from that respect as lambda h, but they're favorable under plausible assumptions with respect to some of these previous bounds. And we also gave some point-wise loss guarantees, which I'm going to describe here, which I think is actually one of the most important aspects of this work. And more recently, Shai with other colleagues have given some negative examples for adaptation in binary classification. These are basically cases where adaptation would not be possible. Some of these examples are really examples in a corner, but really, they illustrate the fact that the problem is difficult. There is a traditional way of addressing the problem of adaptation using what's known as importance weighting. This is basically ignoring the loss function or the hypothesis set and sort of trying to make the distribution that you have on your training as similar to the target. We have tried this, and often it doesn't work. In fact, it's not that it doesn't work, because if it were not working, it would be systematic, it would be nice. It's more that sometimes it works, sometimes it doesn't. So that's really worse. So we try to analyze this because, in fact, the importance weighting is used all over the place in a variety of problems. And let me also say that adaptation and importance weighting also related to boosting. In fact, you can view boosting algorithms very much in those terms. And so we try to analyze in what cases those would work and try to suggest some possible algorithms based on that analysis. And recent work we've been giving simpler and more general learning bounds than those described here with algorithms for actual practical algorithms for tackling this problem. Okay. So let me try to sort of illustrate the discrepancy problem, the discrepancy distance that I'm going to talk about, and the mismatch between distributions that is a problem in adaptation. This is just a simple figure, but it should already give you some idea of what the adaptation problem is. So basically, this is the support of your source, this is the support of P, and really it should be clear that, for example, if these two supports are disjoint, there's not much you can do. How could you learn from data that has nothing to do with the target? So really, the first reaction should be that most of the time, adaptation should not be possible. Okay, so the question now is, in what cases could you actually learn? And then these two distributions are going to be different, not just their support. And the question is, how would you measure the difference between those distributions? And really, one way that should matter is to take into account not just the distribution itself, but also the hypothesis set that you're using and the loss function. And this leads to a particular distance, which I think is really tailored to the problem of adaptation, and which are referring to as being the discrepancy. The discrepancy is a generalization of what's known as a DA distance, which I think has appeared originally in the work of Delfoy et al. And then Kaffer et al. With Shai have really made clear the connection between that and adaptation, and then also use it in their bounds. So the definition is the following. The discrepancy of two distributions P and Q, given a hypothesis set H and a loss function L, is the max over any two pair of hypotheses in an H and H prime of the expected loss of H prime at H measured with respect to P, minus that expected loss with respect to the distribution Q. So why should that be the right way to think about this? Well, first think that H prime is the target. Suppose H prime is a target function. Okay? So really what you care about then is that the loss of your hypothesis H with respect to the target measured on the true distribution compared to the loss measured on your source distributions. This is really what you care about. So it's natural to look at this difference. And but of course you don't know the target distribution. But if you assume that the target distribution maybe is close to the hypothesis set, then you can assume that H prime then would be capital H. Okay? So this is why this is the natural measure of the distance of these two distributions for adaptation. Okay. So this is clearly a symmetric definition. It is also verifying the triangle inequality simply because, well, I guess absolute value verifies the triangle inequality. So it has the triangle inequality property regardless of the loss function. But it's in general not a distance. In other words, you may have, it may be possible that the discrepancy of P and Q would be zero, while P and Q are different. This actually is one of the problems that you would see in some of the counter examples, for example, that Shai has been presenting in some previous work, where you might wish to think that in fact the world is beautiful, your discrepancy is zero, but in fact the distributions are still quite different. Okay, and that comes from both the particular choice of the hypothesis set and the loss function. Okay. So I'll speak a little bit about this in a few minutes. So this general definition holds for any loss function And in particular, it helps generalizing the dA distance to the case of LP losses and arbitrary losses. And one crucial benefit of this discrepancy definition is that it can actually be estimated from finite samples. So, for example, and this theorem is just a special case for the case of losses, LQ losses, you can show that with high probability, the discrepancy, the true discrepancy, the discrepancy between P and Q, is very close to the discrepancy between P hat and Q hat. I'm going to denote by P hat and Q hat the empirical distributions, the distribution corresponding to an unlabeled set of points you would have, and similarly for the source. So it means that these two are very close, provided that the Hadamard complexity of the hypothesis set with respect to the sample S that you receive for the source, and similarly for the target, would be reasonable. So you can think of these as being, if, for example, the hypothesis has finite VC dimension, this would be of the form square root of D over M. Okay, so all of these are basically going to 0 at something like 1 over square root of M.
What's the notation little q there? Like, what's the 4 little q?
Oh, the little q is the q of the LQ loss. So it's just a, for L2 it would be just 2. Okay.
Oh, I see.
Just for the squared loss, q is just 2, and for whatever other loss you want to consider. Okay. So it's just a constant. So this is crucial because it means that you could actually potentially you could compute your discrepancy given an adaptation problem, and based on that, try to see if you're in a favorable case or not. So it's quite important. So now that we have this notion of discrepancy and its preliminary ideas about adaptation, two types of theoretical guarantees could be thought of. One is just like the standard generalization bounds problem. What would be the difference between the average loss of the hypothesis H on Q versus P? Okay, so this is the standard problem you would be thinking of. Another one, which you can think of as being more as a stability problem, but I think is very closely related to what you want in adaptation, is what is the difference of loss between, of course, measured on P, which is the distribution which, that you care about. What is the difference of loss of a hypothesis H obtained when you're training on what you have, Q hat, FQ, Q hat is the empirical distribution, versus the hypothesis H prime you would obtain had you trained on the target distribution. So some data drawn from the target and the corresponding labeling function. Really, that's what you care about, because how could you dream of doing better than even obtaining data from the true distribution? If you were, that would be luck, right? And so both of these problems are interesting problems, and of course there's also just the question of the usual question of learning, what could you even do if, with your hypothesis, how well could you do with respect to the distribution P, but also just standard problems. Okay. So all try to address both of these problems. I'm quickly going to say a few words about them. So first I'm going to present a very simple generalization bound for loss functions that obey the triangle inequality. This can be generalized to even to loss functions that do not obey the triangle inequality, but obey some relaxed version of it. It's quite simple to do this, particularly all LP losses would verify that. And basically what this, so let me first define some notation. H star Q for me is the best-in-class hypothesis in Q, for Q. In other words, it's the one that minimizes the loss when the loss is measured with respect to Q. And similarly, H star P is the best-in-class hypothesis with respect to P. And so what this theorem says is that the loss of your hypothesis H with respect to FP, which is really what you care about, is bounded by the loss of your hypothesis with respect to the best-in-class, plus the loss of H star P with respect to FP. This one you cannot do much about, right? This is basically just related to how good your hypothesis set is. It's the so-called approximation error of your hypothesis set. Plus the discrepancy of P and Q, plus the loss of the best-in-class for Q and the best-in-class in P. So let me just make a few comments about this. This one, as I said, is something that is always going to be there. You can never beat that one. This one is natural. It's basically, it's almost the loss of your hypothesis set. And if H star Q were close to FQ, then that would be just your usual loss. That's the discrepancy term that you find here. And this one is a term that is more problematic because it's not clear that the best in class for Q and the best in class in P would be always close. But again, these two you cannot observe and you cannot measure. Okay? So let me just look at some special cases of this. If, for example, there would be an H star, so H star Q and H star P were equal, let me also mention that these do not need to be unique. The best in class is not unique in either one of the cases, neither for Q nor for P. But
So
if they were...
You could have written it as the minimum overall.
Exact, overall, exact. So you can imagine that I could write it as a minimum.
It was mentioning that it's the minimum and not the maximum of all of this.
Oh, sure, absolutely. So, so if you are in that case, then the bound simplifies to the following, which again, this term is the natural term that you would have in general. This one is the discrepancy, and this term is just the approximation error of your hypothesis. So it becomes natural in that case to think that you would want to minimize your error with respect to the source plus a term that depends on the discrepancy. Okay? So you can see already that the discrepancy distance shows up in this in the bounds. And then of course if you're in a very special case where on top of that the problem is consistent, in other words the target labeling function is in the hypothesis set, then in fact the difference of the loss with respect to the what you care about, with respect to the FP, minus the one measured on P, minus the one measured on Q, is in fact bounded by the discrepancy. So really now the discrepancy becomes the crucial term. So these were all sort of simple bounds that one could derive, and they give you already a little bit of insight. But really what I think is going to be more interesting is to try to look at the second problem that I was mentioning, that of trying to see what happens when you train on some distribution Q to produce some hypothesis H using a particular algorithm versus what you would have had you trained on the true distribution and the hypothesis H prime you would have had in that case. And to do that, I'm going to look at a general class of algorithms. These are algorithms that are minimizing, I mean, you've seen probably most of the algorithms that you see around are of this type. Algorithms that are minimizing a quantity of this kind. Lambda norm of H in some Hilbert space defined by a positive and symmetric kernel K squared, plus the empirical error of that hypothesis H for that distribution Q that you obtain, okay, for the source distribution. This covers a lot of algorithms, support vector regression, support vector machines, ridge regression. A variety of other algorithms are based on the same type of regularized objective functions. So the K here is the positive and symmetric kernel. This is the norm with respect to the Hilbert space defined by that kernel. Lambda is a strictly positive parameter, and as I said, this is just the empirical error. So the question here is, what would happen if you measure, what could you say about the loss of these two hypotheses, H prime and H? And here's the first learning bound that I would like to discuss with you. This one says the following: if a loss L is such that it is mu Lipschitz with respect to its first argument, this is not a strong condition. Again, it holds for all LP losses and a variety of other cases, for example, the hinge loss. So it holds for a variety of loss functions, not the 0-1 loss. And if you assume, and this is an assumption that I will come back to, if you assume that the target function FP is in your hypothesis set, then it says that the loss of the hypothesis H prime that you would have obtained had you trained on the true distribution, minus the loss of the hypothesis H that you obtained when training on the distribution that you have, that loss is bounded by a constant, mu r, times something that depends on the discrepancy between the empirical distributions, p hat and q hat, and eta, which is the maximum difference on your support, on the training points that you have, between the labels that you receive and the true labels you would have had. Let me emphasize this, that there's not much you can learn if the labels you receive on your training set are quite different from the true labels you would have had. It's really, it should be clear intuitively, right? If I could give you just random labels, there's no way you can learn. So you should hope that this distance, this loss between FQ and FP on your support, on the training points that you have at least, should not be too large, okay? Now, if that is the case, if you're fortunate enough that this eta is sufficiently small, then really what this theorem says is quite strong, actually. Because it's not even a generalization bound of the standard form that you see in learning theory. This actually says that the loss, pointwise loss, for any point x and y, for any x and y, the loss of that h prime, the one you would have had you trained on the target, minus the one that you have when training on the source, this loss is bounded by something that depends on this term, plus hopefully something that is small here. So the discrepancy again plays a crucial role here. It's probably one of the things that I would like to convince you of, that discrepancy is an important notion here. But, yes?
I was going to ask if, so if you take an expectation, can you
Improve on that?
improve beta?
No, so okay, so the same loss, because you could think of this analysis often of being a pointwise loss and try to look at the maximum pointwise loss. You could do the same thing in expectation.
Mm-hmm.
The only difference that you would get is talking about the expectation of with respect to the kernel versus its maximum. So it's not going to be very different. It's a question that people ask me quite often. It's natural. But in view of this, learning bound, it's quite natural then to think, is it possible to minimize this term, to minimize the discrepancy between the two empirical distributions? I mean, basically here, if you could even bring this discrepancy to 0, and if eta was really, really small, it really would be guaranteeing that you are succeeding in adaptation, that the loss with respect to h prime of h would be very, very small. So this leads immediately to an algorithm, which we have referred to as being the discrepancy minimization algorithm, and that can be viewed as an adaptation algorithm.
So, what is the dependence on the repeatedness of the loss function?
That's the mu here. So the mu appears here and here. So it's a constant, really, I mean, for the purpose of this.
So is lambda constant as well?
Lambda is the regularization parameter of the algorithm. So it's not usual things that you can see about it.
So you have a trade-off between, I mean, if you make lambda very large, then this difference will be small, but the algorithm will be limited because it's
That's the usual
about
trade-off, exactly. It's sort of the same trade-off you see in stability bounds, where indeed, exactly as you said, I'm going to rephrase it precisely what the problem is. But if fixed lambda, for a fixed lambda, because you could, if you imagine that it's the same lambda you would be using had you had the same quantity amount of data, then it should be sort of comparable. So this leads to an algorithm which consists of precisely seeking to minimize the quantity that I showed before, minimize the discrepancy between the target distribution p hat and the one that you observe q hat. How could you minimize this? There's not much you can do. The distribution that you receive here, the points that you receive are there. You cannot change those points, right? Well, you can not change the points, but you can change the weights you put on each one of those points. So you can seek instead a distribution little q, whose support is the same as the support of q hat, or included in that one, but that puts different weights on those points. And so it's possible that there would be a q whose discrepancy with respect to p hat would be smaller than the discrepancy of q hat with respect to p hat. Okay? So you would be looking for, so I'm going to denote by q star that distribution. If you have a distribution, so you can seek to minimize this. Once you have that distribution q hat, you can then go and reweight your training set by placing weight q star of xi at every point instead of the 1 over m, standard 1 over m weight that you had for each loss. And then the training is basically similar to what you would have in general. So most algorithms can be used, in fact, in a completely similar way by simply multiplying the loss that you have here by q star of xi. Okay. So, so this is a discrepancy minimization algorithm, and according to the theorem that you saw before, this should really quite often succeed modulo those assumptions. And I'm sorry, I went in the right direction. So quickly, if you're in a particular case of a squared loss, then you, just to give you a feeling of how this, how you can find that minimizing distribution, if you call it q prime, this would be searching for a q prime that minimizes this quantity, but the quantity is the discrepancy. The discrepancy is the max over w and w prime in this case of the expectation of this squared loss minus the other one. You can rewrite it in this form and then say that in fact you can replace w prime minus w by any vector u, and if you do that, it gives you the following form, which you can then rewrite by using a matrix, redefining a matrix M of Z, which is an affine function of a constant matrix M0. That constant matrix M0 is basically the average of the rank 1 matrices that you have on the unlabeled points. And each one of these MIs matrices are just the xi, xi transposes for the labeled points. And the zi's here are precisely the weights that you're looking for. These are the weights that you want to put on each one of what you want to learn. So what it means is that the problem of searching for the algorithm can be rewritten as a semi-definite program, which is the following. It's minimizing the norm squared, the norm 2 of m of z, where m of z is an affine function of z. Under some conditions, the fact that z, of course, has to be a distribution, so the z's are non-negative, the sum to 1, and these other definitions I've already mentioned. This is a standard SDP. In fact, a lot of SDPs, it's one of the most standard SDPs that you can think of. So one could think, in fact, it's impossible to solve it efficiently. I'll come back to that in a few minutes. But before that, one could be also interested in knowing if you could use kernels in this setting, which is one of the standard case for these algorithms. And in fact, we have generalized this in recent work by showing that actually if you're using kernels, almost exactly the same SDP needs to be solved. You just have to change the definition of the matrices M0 and Mi. Okay? And then, as I said, this is a standard SDP, and a couple of years ago, we were trying to actually apply this and try to see if it would work. But using the standard SDP solvers out there, even the best ones, you couldn't use more than a few hundred points. You cannot, it just doesn't work. So, so this is, so we've used other techniques for coming up with a better solution for this algorithm, which is based on the ideas of smooth approximations. So I won't have time to go through this, but basically, this is the pseudocode of the algorithm. It's very simple. You would have to solve several quadratic optimization problems. So if you have a quadratic optimization solver, you can just directly use it here. And the idea is to replace the objective function, which is based on the norm 2 of the affine matrix M, approximated with another function that is smooth and easier to handle. This is basically because this function is not differentiable, and it's known to be because when eigenvalues are the same for the matrix, then you won't be able to differentiate. Okay, so this algorithm is actually quite efficient, and maybe I can already actually give you some ideas of how this efficient it is. If you compare SEDUMI, which is the best public solver for SDPs that you could find for this problem, and if you try to run it, this is what you would get, these red points here. And so basically after, I don't know, about 800 points, I think, we just couldn't run it. will just crash. Instead, the blue ones correspond to what you get using the algorithm that I just mentioned, and we could run it for data sets of 10,000 points or more. So this algorithm actually works. You could actually really run it. This gives you basically a general tool for doing adaptation. It's an algorithm. There aren't that many adaptation algorithms actually that are based on theory out there. So this is one that is supported by the analysis that I mentioned before, making some assumptions though. So let me now try to relax those a little bit. Oh, so that algorithm runs in big O of 1 over epsilon. We've proved that. And there's an analysis of this that I cannot describe more. But let me try to go back to the adaptation problem and try to say a few more words about that. Try to look at the most general case. The most general case is the case where the target function f sub p may not even be in the hypothesis set. And so we're still looking at the same family of regularized algorithms. And now the general guarantee for the pointwise loss of h prime minus that of h can be bounded by the following term. It still has the discrepancy as an important term here, but also another term which is delta. And delta now, I've tried to write it in a way that would not be too complicated, but still maybe a bit. So I'm going to go through it with you, your help. It looks a little bit like discrepancy. It's the expectation of h minus fq, where h is the hypothesis, some hypothesis h that you're going to be looking at, but you're going to minimize over h. So it's the expectation of h minus fq times phi sub q. Phi sub q is a feature mapping associated to your kernel function. Okay? So it's the expectation of this quantity minus the expectation of almost the same quantity, except that fq is replaced by fq.
Okay, what is phi sub k?
Phi sub k is a feature mapping associated to your kernel function.
That feature mapping gives you a vector, right?
Sure, so it's a vector.
So
It's a norm.
h of x.
This is a vector. This is a vector. So it's the norm sub k of
Oh,
this
I
vector.
see. It's the norm of the vector.
It's the norm of the difference of expectations of two vectors. And these vectors actually, if you're in a particular case where fp and fq would be the same, even if they're the same actually on your training data, if that would be the same, it would be the same vector. It would be the expectation of the same vectors, one measured with respect to q hat, one measured with respect to p hat. So it becomes very, very similar to discrepancy. The only difference is that fp is not in your hypothesis set
And
now.
also discrepancy was just about the marginals, and here you have the labels.
Exactly.
So
It's a different thing. It's a different thing. I just want to say it has the same flavor in the sense that it's a difference of two expectations for the same quantity in that case, one with respect to q hat, one with respect to p hat. So that's interesting because if you are in the case where p hat and q hat, fp and fq, for example, are the same, which is a strong condition, but it would hold if you're doing sample bias correction, it would hold approximately in some cases as well. And even in the approximate case, that's going to be interesting. Because think about the following. The algorithm that I just described to you can minimize the discrepancy between p hat and q hat. Suppose you can actually minimize this to the point where if you have enough unlabeled data, this quantity will become really, really small. In some cases, when this quantity becomes really small, you can show actually that the expectation with respect to q hat and the expectation with respect to p hat of some family of functions would also become very close. When that is the case, it means that actually when you're minimizing this term, you're almost also making this other term small. Okay, so I'm going to discuss this in a second. Yes?
I have one question. This discrepancy, somehow if unlabeled sample is much bigger than the labeled sample, then discrepancy grows with this difference in size.
Mm-hmm.
So when I add
Discrepancy grows, you mean the empirical discrepancy or?
the empirical discrepancy, somehow if you compare two distributions, one of them is on a small domain, and the other one is on a big domain, then there is some inherent discrepancy between them.
So
due to the fact
remember that
they have
this-
different supports.
Let me sure. So they have different supports, and you could. So there's a lot to discuss here. This discrepancy, when you try to minimize it, actually. So this is work that we've done. In some cases, you can show that it can become really close to zero, but that will depend indeed on the relative supports of Q hat and Q
Okay, so
hat.
that was,
So of course, again, if you're in a bad case, you will not be able to make this small. But let me actually make this in more general terms. In the previous algorithm that I mentioned, you minimize the discrepancy. Once you have minimized it, you can actually look at the values that you obtain. If the value of the best empirical discrepancy that you obtain is actually still not very small, well, you're not in a good case. Actually, you should not do adaptation there. This is another message for this work, actually. You should be in some cases where you're rejecting. Adaptation in many cases should be just rejection. Don't try it. It's not going to work. So
it's a lower bound for a specific algorithm. Not a
it's
lower
for the
bound.
particular algorithm. It's for this
It doesn't tell you
algorithm.
that no algorithm will be.
No, it would be for this. It's still a wide family of algorithms. So what I want to say here is that in some cases, for some hypothesis set and some loss functions, you might actually be able to make this very small. If you make this very small, actually you might also make this other term very small. This is interesting, okay, because you don't really have access to the labeling function. But because the p hat and q hat might become very close, actually that expectation that difference of expectation could become very, very small. This is really good news for adaptation.
Actually, why? I mean, one question about delta. Why the min there? I mean,
Well, the min is over h, because you can actually choose the best hypothesis here to make this as small as possible. I could have just used instead of h, just say the best in class for p or the best in class for q. But you can make it as small as you want. You can choose the best one.
I think it's quite similar to our lambda, which was the minimum of all h's of the arrow on the source and the arrow of the target.
It's similar, except there you have a sum.
Yeah.
It's similar in spirit, but it's actually different.
I know.
Because there you have a sum. Here it's actually a
Right,
difference.
so you don't get the three factor that we had.
Exactly. You actually avoid that exactly. You can see that, right? You avoid it because actually this is going to become zero if p hat and q hat are close.
Right.
So this actually is a nice little. So let me
it's nice
show
to
you.
be able to take just the expectation there as well, right?
Yes, because again, okay, so let me just briefly tell you about one more thing, and then I'll wrap up. I do want to mention that in some cases, which is actually a standard case where people are using their algorithms for this kind of objective functions, the case we're using Gaussian kernels, for example, then actually discrepancy is a distance in that case. And when discrepancy is a distance, what it means is that if you could really minimize the empirical discrepancy of p hat and q hat down to almost zero, in fact, those distributions would become the same. Okay? So I don't have time to go through the proof of this.
But there's a big cost to it.
This is what?
There was a big cost to it.
There's a huge cost because you're using Gaussian kernels,
Right.
which would be a strong family of hypotheses. But nevertheless, let me just be clear. A lot of people are using Gaussian kernels in practice, right? So.
But the discrepancy distance will become big when you have such a big family of hypotheses.
So it's whatever it's the algorithm that you're using. No. So the discrepancy between the empirical discrepancy might actually become very close to zero, depending on what setting you are in. Okay. So what's important here is that this shows that it's a distance, but what's more interesting is that if you manage to even bring the discrepancy, the empirical discrepancy down to epsilon, what you can show is that actually then in that case, the difference of expectations between those labeling functions that I mentioned as well, if fp is equal to fq, would also be down close to epsilon, be also very small. So then you really are making both quantities small. Okay, so I'm just going to stop here. There's a lot to discuss on these learning bounds to see in what cases this would work. We have done some experiments using a data set of John for starting with several domains, books, DVD, electronics, and kitchen, to compare, to see how this algorithm actually works, the one that I mentioned to you, under the assumptions that we looked at. And well, basically, quickly speaking, it shows that it actually works in many of those cases. This would be the ideal error that you would have. and the error goes down as you get more and more unlabeled points. Okay, and of course this depends on different pairs of domains. Some domains are more difficult than others, but this is again related to the discrepancy of the distributions. There's a lot to say still about adaptation, lots of other problems that are open out there. One of the things that I wanted to say is how discrepancy becomes a crucial notion in this analysis. Another one is that not everything is negative. So even if you are in some cases you're in a bad case, and as I said, you should reject adaptation. You should not just not do it, at least for those algorithms. But you also see that the bounds are directly depending on quantities that are favorable or not, depending on the labeling functions and depending on the difference of the distributions, which is what you should expect.
So can you show these results as a function of the discrepancy? What happens if it's large?
So, so I don't have the numbers here, but basically in these cases where you see that, for example, for this task, this is adaptation to books. So the red one here is what you would have if you were just training on books and testing on books. And this one is the blue on DVD. So DVD, for example, on books here, you see DVD is not doing very well. It still does better as you get more and more unlabeled.